This is a real quick conceptual check, kind of recap of some discovery process for infinite geometric series. I'm going to try and make it independent of the discovery we did, but it's definitely fits best with what we did in class. The main thing is that we come to this place where we say, if you have an infinite geometric series, a plus ar squared plus dot dot dot, and you continue it forever, then first of all, that has a meaning. That's the big deal. And that there's a simple formula for it, as long as the size of r, the absolute value of r, is less than 1. So it's between -1 and 1. If it's not, if r is like 2 or -5 or something, these terms are going to grow and possibly oscillate in sign. And it's going to be very hard to see how there could possibly be a meaning here. And we don't assign a meaning to that. Some people do with very weird techniques, but we're not going to do that. So let me just get at it through examples. 1, this is my favorite example to start with, 1 plus a fourth plus a half plus a fourth plus an eighth plus a 16th. In other words, the sum, if I want sigma notation, which you don't have to do, but it's to infinity, of 1 over 2 to the k minus 1. If that doesn't make it more palatable to you, ignore it. Okay, it's just that sum. Okay, the claim is, well, let's see, the a is 1, the ratio is 1/2. It's the ratio here. Now, it's not just always the second term. It's the ratio, but here that happens to be the second term. And I get 1 over 1 minus a half, which is 2. What does this mean? Well, it means that if you take any finite sum, you're going to get a number close to 2. That's the first thing. That if you take it further and further and further, way out, like to 1 over 2 to the 100th, you're going to get ever closer to 2. And in particular, you can make any finite partial sum where you actually do stop and you can actually really sum it in the ordinary way, arbitrarily close to 2. Which means a practical way to say this is think about, for your particular application, what kind of accuracy do you need? Do you need 4 decimal places, 12 decimal places, 1,000 decimal places? No matter what you stipulate, we can add enough terms up here and just be less and less lazy to get close enough to 2 to satisfy that. It could be 2 minus 1 over 2 to the millionth if we wanted it. Okay, there's a lot of stuff here. It gets close to 2, ever closer to 2. It can be made arbitrarily close to 2. That's a whole paragraph worth of stuff. The way we summarize that is simply that if you add up, quote, let me put my little air quotes, quote. If you add up the whole thing, you just get 2. That does not mean we've figured out a way to actually add them all together. It's a shortcut. It's kind of, I hate to say a trick, but it's a very cool shortcut. It's an end run around the idea of how would you ever actually add them up. Another way to say it is that there's a trend here that if we do this on a number line, I think it's really helpful to look at this pictorially. We go from 0 to 1 to start the series. We had nothing, and now we got the first term. Then we go to 1.5 or 3 halves, 1 and 1 plus a half. That happens to be halfway of the way to 2, which we already have a suspicion is our goal. Then we go halfway again, because we're adding a quarter, and that's halfway to 2. And then we add an eighth, and that's halfway, and halfway, and halfway, and halfway, and halfway, and halfway. And so another way to describe what we're doing is we're always halving the distance to 2. That hopefully makes it clear that you can describe it as a process whose goal is 2, even though it never gets there at any finite stage. So the goal, or the trend, or in technical mathematical terms, the limit, that is defined to be, that's what we use as a definition of the infinite sum. That's the shortcut, or that's the kind of the, I don't know, think of it as like short-circuiting this infinite process. We actually try to cleverly figure out what does it seem like it's going towards, what it would like to get to if it could ever get there, but it never actually gets there in any finite time. And we declare that to be the infinite sum. So that infinite sum, off to infinity, it's equal to 2. A lot of people want to say that's approximate, but by definition, we're saying it's equal, Because we're defining a new thing. This is a new concept. This isn't one of the finite sums. We're defining something new, and we get to define it. The main thing is it a smart definition? And to some extent, you have to kind of take on faith that that's not a crazy definition. Okay. What's another example? This is one of the examples I like to do. 2 plus 2/3 plus 2/9 plus 2/27. I'm not even going to worry about sigma notation. I am going to do the picture first, though, because it's not, again, a nice picture. I'm going to conveniently put it on a number line between 0 and 3, because I know what the answer is going to be. First, you go to 2 to start it out. Then plus 2/3, that's taking 2/3 of the remaining distance to 3. That's the 2 plus 2/3. Or in other words, the remaining distance left to 3 is now 1/3. Adding 2/9, that's 2/3 the way to 3. The remaining distance in here is 1/9, and so on. What happens is at any stage, the remaining distance to 3 gets thirded, gets reduced by a third. So what this is a process that's clearly, well, if you believe what I just said, but you can check it if you want, that's really trending to 3. It's trying to get to 3. And so my claim is the infinite sum. By definition, we short circuit that infinite process. We don't concentrate on the process or think of it as something that's in progress. We actually cut it off and say, you know what, your trend, what you're trying to get to is 3, and we will declare that to be the value of the infinite sum. Let's see if it works with our formula. A equals 2. R equals, not 2/3. This is a mistake my students always make. Excuse me. I'll edit that out someday, maybe 10 years from now. The ratio, make sure you can do the ratio correctly on one of these guys. The ratio is the ratio, this over this, that's 1/3 here. And so the infinite sum is just 2 over 1 minus 1/3. That's 2 over 2/3, and that's 3. Okay. For my money, if you believe this geometric picture, which I know I went through kind of quickly, I think that's more convincing that this should be 3 than some formula somebody got out of a book of A over 1 minus R. Now, there is a nice algebraic derivation of this that says, yeah, this really should always work. But if that doesn't convince you, you might want to just look at the geometric picture again. Let's do another one that's really a one I like to do. 3/10 plus 3/100 plus 3/1000 plus 3/10,000 plus, I picked this one specifically because it's incredibly easy to write the decimal. That's 0.3. Oh, plus another 3, plus another 3, plus another 3. Oh, this is exactly a repeating decimal. Now, we've been told for a long time that that should equal 1/3. But it's something you should be really suspicious of. Wait, this infinite repeating, what does that mean? Well, what it means is, by definition, it's this. It's the infinite, it's the sum of an infinite geometric series. And what does that mean? It means look at this number, and then this, and then this, and then this. Those are easy to calculate, or at least straightforward to conceptualize. And look at the trend they're going to. So in other words, you're looking at 0.3, 0.33, 0.333, 0.3333, and you don't focus on each one of these or think of it as a process that's continuing. You look at what's the trend. And the claim is the trend is what you get when you divide 1 by 3. Okay. Let's see if this accords with our usual formula. Okay. Oh, and let's look at the picture. Okay. Here's 1/3. Here's 2/3. 0.3 is a bit shy of 1/3. And 0.33 like this, 0.333. So hopefully it's plausible that it's really getting close to 1/3. That's maybe not the best, the most convincing derivation, but it's the same picture as we had in the other cases. Here, A is 3/10. Okay. Now, hopefully, I don't know. I think most people believe, once you believe that there is a rigorous way to define this, I think most people are like, okay, I now trust that it really is equal to 1/3. But if you're skeptical about it, that's fine. R is just, 3/100ths over 3/10. Oh, that's just 1/10. The whole point is every time I'm just reducing it by a factor of 10. And so A over 1 minus R, that's supposed to be the sum. See if I can fit it in here. 3/10 over 1 minus 1/10 is 9/10. If you work that out, 8 is 1/3. Okay, so the formula is according with what we were told long ago about what that magic repeating decimal is. Now, another one that's freakier to people is 9/10 plus 9/100ths plus 9/1000ths plus, All right, so that is 0.9 repeating, or if I want to write it out, 0.9999 dot dot dot. Okay. Now, that one, definitely people get a little more freaked out by. Let's look at the, this description is like a path. I claim this is a path with goal equal to 1. What's going on is I go 9/10 of the way to 1, and I get 0.9. What's left is 0.1. And now the rule is I go 9/10 of that. Well, 9/10 of 0.1 is just another additional 9/100ths. So I get up to here, and that's 0.99. And then I go 9/10 of the way to that, and I get 0.999, etc. So as a process, this, then this, then this, then this, the sequence of partial sums of this, guys. As a process, it's something that approaches 1 but never gets there. A lot of people would like to say that's their answer for what this infinite repeating decimal is supposed to be. But the deal is, by definition, we don't look at the process, we look at the trend it's going towards, its goal point. By definition, to make this actually have a definition at all, we say that's the goal. Yes, the process, if you focus on all the finite details, it never gets to 1, but the goal is 1. And so this really, really, really is true. Okay, and this is one of these cases where people are like, I don't believe that. And usually it's because people are mistaking the process, and that's the sequence of finite partial sums, with the goal, where you actually have to really think about it, and you actually have to do what's essentially a limit calculation. So it's fairly deep to do that. One more. I know this is a little bit on the long side, but I think it makes sense to just put this all in one video. What about 26 over 100 plus 26 over 10,000? This is more random. The other ones were all special. 26 over a million plus 26 over, I'm going to write it as exponential notation, plus. The reason I wrote this out, it's fairly similar to the previous two examples. That's 0.26. Oh, plus the same thing moved over decimal place, 2 decimal places, 26, 26, 26. So that's a repeating decimal, but with a double digit repeater, 0.26, and the bars over both of them because it repeats. Okay. Now, you might have been taught a method for evaluating this, okay? And now we have a more rigorous justification for that. A is 26 over 100. R is 1 over 100. S is just going to be A over 1 minus R is 26 over 100 over 1 minus 1/100th. I'm going to multiply both top and bottom by 100. That's probably a pretty good way to do it. 26 over 100 minus 1, 26/99. So, and that doesn't really reduce, so that's what it is, 26/99. So if you put in 26/99 in your calculator, you're going to get not this infinite repeater, because calculators don't do that. You'll probably get something like that, 2626262663 maybe, because it's going to round it off. Okay, but really it should be giving you an infinite repeater. Okay, just one thing. The usual way people demonstrate this, being pretty cavalier about ideas of infinity, is you say let's let that equal x, or let's say s. That's what we're just doing. And then notice that 100s is 26.26, and then do 100s minus s. What it looks like is that all these decimals cancel out except for the 26. And that actually gives you the right answer, but it's pretty darn sketchy. If you just write this down and say, I think this has a meaning, and then you start doing algebra with it, you're really on thin ice. And so these ideas of limits and summations really put it on a more firm footing. But in any case, you do get the right answer. S is 26 over 99. But there's analogous manipulations that you'd like to do when you do more about infinite summations and series in a calculus situation, where you can start doing this kind of stuff and be too cavalier about it and get an utterly, utterly wrong answer. So it's something to be careful with.